Swayam Prabha. Digital India. Educated India.
Welcome to lecture 15. Today we are going to discuss about some application of Hillbert Nullstellensatz theorem. So, let us see. So, in the last lecture we have seen the Hillbert Nullstellensatz theorem, which says that there is a 1-1 correspondence between the points in C n and the maximal ideals in the polynomial ring in n variables over the field of complex number. So, what was this correspondence between the points in C n and the maximal ideals in the polynomial ring? So, the correspondence was given by, suppose you start with any point a bar, which is a 1 up to a n in C n, then you can associate a maximal ideal with this point. The maximal ideal I am denoting by m a bar, which is nothing but generated by n many linear polynomials generated by x 1 minus a 1 x n minus a n. So, for a point in C n a bar, I am denoting, I am attaching this maximal ideal m a in this polynomial ring, and further we have proved also that this if you start with a maximal ideal in this polynomial ring in C x 1 x 2 x n, then every maximal ideal is of this form. So, you can associate to every maximal ideal one point in a bar. So, this gives you the 1-1 correspondence between the points in C n and the maximal ideals of C x 1 up to x n. Here it is very important that we are considering this polynomial ring over the field of complex number. If we would like to replace this, then we have to replace it with an algebraically closed field. So, that is something that if it is not part of the, I am not going to define it right now. Later in some other course you will get to know what is algebraically closed field. It has having the property that if you consider a polynomial, then all the roots of that polynomial inside C. So, that is the algebraically closed field, that is the meaning of that. Okay. So, now let us give some application of Hillbert Nullstellensatz. So, before that let me define some concept from algebraic geometry, which is known as variety. So, what is a variety? So, let V be a subset of C n, and if V can be defined as the set of common zeros of finitely many polynomial functions, set of common zeros of a finite number of polynomials in n variables, then it is called a variety. That means what? That means if I denote this V is said to be a variety if it is nothing but the set of common zeros of a finite set of polynomial. Say f 1 up to f r is a set of finitely many polynomials, and by z I am denoting the common zeros of this polynomial. So, this is nothing but the solution of this system of equations f 1 equal to 0, f 2 equal to 0, f r equal to 0. So, variety is nothing but the set of common zeros of a finitely many polynomial equation. It is very important that all of these f i's are polynomial functions. So, let me just write down that these f i's are polynomial over x 1 up to x n over the field of complex number. So, this is how we have defined the variety. So, this is one of the basic object if you want to study algebraic geometry, and this Hillbert Nullstellensatz we will see actually establish the connection between algebra and algebraic geometry. So, let me first give you some example of variety. So, for example, if I consider the complex line in C2, then all the points lying on that line forms a variety, the set of points which are lying on that line. So, a complex line in C2 is nothing but the 0 of single polynomial of the form a x plus b y plus c. So, this is the set of 0 of a single polynomial which is nothing but the points lying on this line represented by this equation. So, this is an algebraic variety. So, this is a variety. So, this is one example of a variety. Now, if I consider any point in C2, then I can view it as the solution of two straight lines. So, for example, every point say A comma B in C2 is a variety, as I can view this point A B as nothing but the set of common zeros of the equation x minus a equal to 0 and y minus b equal to 0. So, x minus a equal to 0 is an equation, polynomial equation, and y minus b equal to 0 is another polynomial equation. And if you consider the set of common zeros of these two polynomial equations, then that is we will get the point a b in C2. So, therefore, every point is in fact defines a variety in C2. So, this is another example of variety. Now, let me give you something which is a little bit non-trivial example. So, for example, if I consider SL2C, what is SL2C? SL2C is nothing but the set of all 2 cross 2 matrices with complex entries such that their determinant is 1. So, this is nothing but the collection of the matrices of the form A11, A12, A21, A22 such that all these Aij are complex numbers and the determinant of this matrix. So, that is nothing but A11, A22 minus A12, A21 is equal to 1. So, the set of points in C, so we can show that this defines a variety in C4, because if I take a point in C4 say A11, A12, A21, A22 which satisfies this equation, then it will gives this matrices, this set of points, will give you this set of matrices. Therefore, this defines a variety. So, here we say that this is a variety in C4, as we can view it as nothing but the zeros of this single polynomial A11, A22 minus A12, A21 minus 1. So, this is the polynomial, this is equal to 0. Okay. So, this gives you the set of matrices with determinant 1. So, SL2C is also defines a variety in C4. Okay. So, we have given some examples of variety. Now, let us see some application. So, one of the application is the following theorem of Hillbert Nullstellensatz. So, let me state the theorem. So, the theorem says that let f1, f2, fr be polynomials in the polynomial ring C x1 up to xn. So, these are polynomials in polynomial ring over complex numbers in n variables, and say I am considering the variety V to be nothing but the set of common zeros of this finitely many polynomials. So, f1, f2, fr. So, V is the variety because this is the set of common zeros of finitely many polynomials, be a variety, and let I be the ideal generated by these polynomials f 1 up to f r. So, this I is an ideal in the polynomial ring in n variables and V is the variety in C n. Okay. So, this is a subset of C n, set of common zeros of these polynomials. Then it says that the maximal ideals of the quotient ring, let me denote that quotient ring by R, which is the quotient ring of the polynomial ring via this ideal I. So, we are trying to identify the maximal ideals of quotient ring with the points in the variety. So, what this theorem says, that the maximal ideals of this quotient ring are in bijective correspondence with the points in the variety, V. So, what does it say? It says that how many maximal ideals will be there, as many points are there in the variety V. So, V is nothing but a set of points which are defined as the set of common zeros of finitely many polynomials, and to every point in this variety we will get a maximal ideal in the quotient ring. So, this gives you in some sense the connection of this algebra with geometry by attaching the points in the variety with the maximal ideals in the quotient ring. So, let us go through the proof of this, but before proving this theorem, so let me So, let us go through the proof first, then I will say some remark about this statement of this theorem. So, the maximal ideals of R means that is quotient ring. We know how does maximal ideals of the quotient ring look like. So, by the homomorphism correspondence, what do we know? We know that the ideals of this quotient ring are in 1-1 correspondence with the ideals in the ideals of this polynomial ring which contains I, right. Therefore, the maximal ideals will be nothing but maximal ideals of this polynomial ring containing I. So, the maximal ideals of R corresponds to maximal ideals of this polynomial ring in n variables containing this ideal I, which contain I. So, that means every maximal ideal of R will be of the form, it should be a maximal ideal of this polynomial ring containing this ideal I. Therefore, an ideal if contains I and I is generated by nothing but this R polynomials, that means each of these R polynomials should belong to that maximal ideal. So, an ideal will contain I if and only if it contains the generators. If and only if contains the generators, and the generators of this ideal I are nothing but the polynomials f1 up to fr. So, if a maximal ideal contains I, then that maximal ideal will contain all of this polynomial f1 up to fr of I. Now, what do we know? The maximal ideals of this polynomial ring, the structure we know. So, now the maximal ideals of this polynomial ring x 1 up to x n is of the form the maximal ideals are of the form M A, which is generated by this n polynomials for some point a 1 a 2 a n. So, the maximal ideal is of this form for some point a bar equal to a 1 up to a n in Cn. This is by the Hillbert-Nullstellensatz theorem. We have seen in Hillbert-Nullstellensatz that every point in Cn can be associated with a maximal ideal, and every maximal ideal is of this form corresponding to a point in Cn. So, since we are looking at the maximal ideals of C1 x2 xn, therefore, it has to be of this form for some point a bar in Cn. But now, this Fis belongs to this maximal ideal. What does that mean? So, Fis belongs to this maximal ideal. That means, this Fi should be I should be able to write down this Fis as combination of these linear polynomials x1 minus a1 xn minus an. So, that is this Fi can be written as some combination of x1 minus a1 plus L2 x2 minus a2 plus Ln xn minus an, where these Li's are nothing but polynomials in the polynomial ring C x1 x2 xn. So, each of these Fis I have written as combination of these n linear polynomials. Then if I evaluate this polynomial Fi at the point a bar, what do I get? This is true for all I equal to 1 to r. Now, if I evaluate this polynomial at the point a bar, that means a1 up to a n, then you can see if I substitute in place of x1 a1, in place of x2 a2, and in place of xn if I substitute a n, then this equation gives me 0. That means, Fi evaluated at this point is equal to 0, and this is true for all I from 1 to r. That means, it says that this a bar is a common solution of this system of equation. That means, a bar belongs to the variety V. So, this implies that, which implies that this a bar belongs to this variety V. So, what I have proved now? I have proved that if you start with a maximal ideal in this quotient ring R, then that maximal ideal will corresponds to some maximal ideal of the polynomial ring, which will be of this form, and this maximal ideal should contain I. If it contains I, that means it will contain all the generators of I, and the I is generated by Fis. Therefore, all these Fis should belongs to this maximal ideal Ma. That means, these Fi can be written as linear combination of these linear polynomials, and hence all these Fis, if I evaluate at this point a bar, then it is 0. That means, a bar is a common solution of this system. That means, a bar is in V, and this is true if you the reverse process if you go through, then that is also true. So, this proves that every maximal ideal of this quotient are in bijective correspondence with the points in the variety. Now, as a remark, we will show that the algebraic property of this ring R is in fact closely related with the geometric property of the variety. That means, the number of points in the variety, it gives you the count on the number of maximal ideals in the quotient ring. So, as a remark, we can say that the algebraic property of the ring R is nothing but that quotient ring. These the algebraic properties, basically I should say algebraic properties of this quotient ring are closely related. These are closely related with the geometry of the variety V. So, therefore, the studying the solution of system of thus studying the solution of a system of equations is equivalent to study the variety, is equivalent to study the variety defined by the set of polynomials. That means, if I would like to see whether a system of polynomial equations have some non-trivial solution or not, or whether there are finitely many solutions, whether there are infinitely many solutions, how does the solution of a system of equation look like, then we have to basically look into the variety. So, and looking into the variety, we have seen that the number of the points in the variety corresponds to the maximal ideal of the quotient ring. So, that is the relation between the algebra and geometry. So, now we will see the following, we will try to investigate first whether a set of set of polynomial equation have some solution or not. So, in order to do that, so the question, the question that we are asking is whether a system of polynomial equations have any solution or not. So, for a system, does there exist any solution for a system of equations or not? So, in order to answer that question, we have to look into the variety of that. So, suppose I have this equation, say f 1 equal to 0, f 2 equal to 0 and f r equal to 0. These are the polynomial equations, and we would like to see that whether this system has a solution or not. That means, we are interested in investigating whether the variety which is defined, whether this variety V which is defined by the set of common zeros of these polynomials is non-empty or not. So, if it is empty, that means this system of equations does not have any solution, and if it is non-empty, that means there exists at least one solution for this system of equation. So, basically this leads you to investigating when this variety is empty or non-empty. So, before proceeding further, let us recall what we have already seen. We have seen that if we are in a ring, then every non-unit ideal is contained in a maximal ideal, right. So, let us just recall that. So, we have already proved this following theorem. So, let R be a ring, then every ideal I of R which is not the unit ideal, which is not the unit ideal is contained in a maximal ideal, is contained in a maximal ideal. So, this is what we have already seen by showing that in a non-zero ring always maximal ideal exists, and maximal ideal is a proper ideal, that also we have seen. So, it says that every non-unit ideal is always contained in a maximal ideal. That means, now if we have, by the previous theorem, we have associated the points in the variety with the maximal ideals in the quotient ring. Now, if the variety is empty, that means there is no maximal ideal in that ring. So, that means what? That means the ideal has to be the unit ideal. So, as a corollary to this, I can write down the following, that the only ring R having no maximal ideal is the zero ring. Because in the 0 ring we know that the multiplicative identity is same as the additive identity, 1 is equal to 0 in the 0 ring. That means, there is only one ideal which is the unit ideal, and therefore, there does not exist any maximal ideal. So, if there is a proper ideal in that ring, then it should always be contained in a maximal ideal. That is what this theorem says. So, if a ring does not have any maximal ideal, that means that ring has to be the 0 ring. Now, we are in a state to prove that when the variety will be empty. What does it mean in terms of ideal? So, let us just write down the statement of the theorem. It says that, maybe this I can put it as a corollary to the previous theorem. So, this is the corollary of a previous theorem. So, let f 1 up to f r are polynomials in x 1 up to x n. If this system has no solution, if this system has no solution in C n, then it means that the ideal generated by f 1 up to f r has to be the unit ideal. That is saying that 1 can be written as combination of these polynomials. And the proof is simple. So, how does the proof follow? So, the proof, if you look, so that means if it does not have any solution, that means the variety, that means the variety of this set of polynomial is empty. That means, there is no point in the variety, that means there is no maximal ideal in the quotient ring. So, it says that, which means there is no maximal ideal in the quotient ring this. And we have seen in the corollary that no maximal ideal means what? That the ring is the 0 ring. That means, R is the 0 ring. So, R is the 0 ring means what? That means that the ideal I has to be the unit ideal. That is equivalently saying that the ideal generated by this set of polynomial is the unit ideal. So, I am able to show that when a variety will be empty, if the ideal generated by that system of equation defines the unit ideal, then it will be empty. So, this has many applications. So, let me quickly give you one example which is useful. So, consider this polynomial. Say f 1 is the polynomial x square plus y square minus 1, f 2 is the polynomial say x square minus y plus 1, and f 3 is the polynomial which is nothing but x y minus 1. So, if you draw the curve of this polynomial, then you can see that there is no solution, common solution of these 3 equations. So, the variety, the set of common zeros of, so V, which is nothing but the set of common zeros of f 1, f 2 and f 3 is empty. So, then by applying the previous corollary, we can say that then it imply that the ideal generated by f 1, f 2, f 3 is the unit ideal. So, that means I should be able to write down 1 as combination of these polynomials L 1 f 1 plus L 2 f 2 plus L 3 f 3. But it is not very straightforward to see that this ideal generated by f 1, f 2, f 3 will be the unit ideal, unless otherwise we do not know the correspondence between this variety and the points in the variety and the maximal ideals in the quotient ring. So, that is why this is useful in identifying, because by looking at the variety we can conclude, since the variety is empty, we can conclude that this ideal is not a proper ideal, it is in fact the unit ideal. That is why it is useful for us to investigate or apply Hilbert Nullstellensatz in these cases. So, today I will stop with this one. These are the references that I have used for today's lecture, and thank you.